Okay, so with this, an implicit differentiation problem, we're going to need this to move on to what's called related rates. And again, we really have to mind our variables and see what's going on here. So we have find the dr over dt if v equals 4/3 pi r squared. Now you're probably like, the Shriver's made a mistake. There's no t in this whole problem, so how can we do it? I did make a mistake. This is what we're doing now. This is, what does this look like?
A cylinder?
Oh, it's actually should be cubed, actually. Let's make it
Now
cubed.
it's a sphere.
Now it's the volume of a sphere, right? It is. I wrote it. I know that. I mean, it's not correct. But V's the volume, R's the radius. Now, as the radius changes, will the volume change?
Yes.
Yeah. The question is, how much? Right? So what this is saying is this is find the change in the radius divided by the change in the time. Okay, so that's we're writing a function for that. So maybe you're blowing up a balloon, right? Does the radius change over time? Sure. Would the volume change then? Sure. So that's what we're trying to do here. So that's what this means is we're going to take this and do the derivative with respect to t. Now we have to assume that v is a variable and that r is a variable. Now 4 and 3 are constants and pi is a constant. A lot of times people forget that pi is a constant and they spend, like whenever you see d pi over dt, it means that they thought that pi was a variable, but it's not, right? So let's go ahead and try this. We're going to take this equation. We're going to take the derivative with respect to t of both sides. Now at this point, this left-hand side is just going to become dv over dt, right? That's what we're used to. So that's the change in volume with respect to time. And then over here, before I take this derivative, I'm going to go ahead and take the 4/3 pi and just set it outside. And I'm actually just going to write it as 4 pi over 3, and the derivative with respect to t of r cubed. So again, because this can get a little confusing and there's going to be multiple variables, it's really organizing is important. Yeah?
So will you never have to take the derivative of 4 pi over 3? How does that work?
Well, if it were just this, you'd take it, I mean, it's a constant derivative, would just be 0. But this is a constant multiple, so we're just taking advantage of our property that says that you can put a constant multiple outside and then multiply it back in later. So good question. So here, the left side's good, 4 pi over 3 is good. The derivative of r cubed with respect to t, well, you take the derivative of r cubed like you would anything else, x cubed, right? So we're going to get 3r squared. But then since the r does not match the variable t, we're going to get a dr dt. So we get dv over dt is 4 pi over 3 times 3r squared times dr over dt. Okay, so that looks pretty good, right? This is what we're trying to solve for. Now at this point, you could just like start randomly dividing things and you could get dr over dt by itself, but we're actually going to use it for something, so it'd be nice if it's in a form that's relatively usable. Now, looking ahead, this we're probably going to put in a whole number for, or its own value. But what I would recommend we do here is go ahead and multiply these two pieces together. So dv over dt equals 4 pi r squared. And the 3's cancel, correct? So we get 4 pi r squared times dr over dt. Now at this point you could divide by 4 pi r squared. What I like to actually do though is, if I have anything that even looks remotely like a fraction, I choose to multiply by the reciprocal. I think it just looks cleaner. It's easier for me to understand. So this is 4 pi r squared. I don't want it on the right-hand side. So I'm going to multiply both sides by its reciprocal. Showing a bunch of work here. So these will cancel out, correct? So then we get 1 over 4 pi r squared times dv over dt equals dr over dt. Okay. Yes?
You lost me at the reciprocal thing.
Yeah.
Okay. Yeah, so all I'm doing here is I want to get this to not be on the right-hand side.
Okay.
Okay? Now I could have dv over dt divided by that, and it wouldn't be terrible. Right? If you just would have divided, you would have got dv over dt divided by 4 pi r squared equals dr over dt, which is not bad, but I don't love like having a fractiony looking thing in a fraction. So all I did is I know that if I take a number or a value times its reciprocal, these cancel.
Oh, because since you did on one side, it's different.
Yeah. So it's a simple case, but this is like if you had 2/3 x equals 5, right?
Yeah.
You
I
could
think we just
multiply
put all
both
the
sides
letters.
by 3/2. Oops.
I think just like all the letters just like confused me for a second.
Oh yeah, it's like a bowl of alphabet soup up here. There's a lot of letters. That's why it's really important to keep attention and make sure that you don't, because a problem I tend to have too is sometimes my dt's will become dx's by the end of the problem because we're so used to using them. So you just really have to be deliberate with these. Okay, so from our worksheet we had our second example, which is really like the one we just did. So if you're watching this video and working through it in class, stop the video, try it, see what you get. So we had find the derivative with our dr over dt if a equals pi r squared. So we're back to circles now, right? We had sphere, now we have circle. So I'm going to take the derivative of both sides with respect to t. Now, would it be nice to pull the pi out? I think so. Okay, so it's just a constant. Again, you got to really kind of hammer that home because it's easy to forget. So over here, the derivative with respect to time of area is just written as dA over dt. And then pi. And then here, when you take the derivative of r squared, we're going to get 2r. Yes, and we know that we have to put the dr over dt because r and t are different letters. So we're going back to, they're different. So. Now at this point, we're asked to solve for dr over dt. So let's just take a second, kind of clean this up. I'm going to write it as 2 pi r because I feel like I've seen that somewhere before. And at this point, again, you could divide dA over dt by 2 pi r. It wouldn't be wrong. I'm going to multiply by the reciprocal. So 1 over 2 pi r times dA over dt. 1 over 2 pi r times 2 pi r dr over dt. Again, just showing a lot of work there. Those will cancel out. So we get dr over dt is 1 over 2 pi r times dA over dt. And again, what this means is what we're going to look at. This is for some change. This is if you take these, they're for a given radius. If you change the area, so this would be some rate, right? Area, square inches per second, square inches per minute, right? It's going to give you some result, which would be the change in the radius per time unit, inches per minute or inches per second, whatever unit is. And notice if this was square, like say square feet per minute, you divide it by feet right here. So you would just get feet per minute, which is good because radius should be a linear measure where area should be a square measure. So this should make sense too in terms of the units. It's a nice way to check things. So our next example here, very similar to what we just did. It's still a derivative with respect to time. But in this case, notice we have x squared times h. We have two variables. It's going to be harder, right? We had one variable before. So this would maybe be, I don't know, the volume of a box with a square base, right? X by x base, h is the height, this would be the volume. So with this one, if we're going to ask to find the derivative of x with respect to t, the first thing we know we need to do is take this piece and just take the derivative with respect to t. So to do that, the derivative with respect to t of the volume, and the derivative with respect to t of x squared h. Now at this point, the left-hand side will just become dv over dt, right? The change in volume for a certain amount of time. And then over here, we have two functions multiplied together, like a product. Right? And since we have a product, we should use the product rule.
I say no.
Veto the product rule. Okay, so x squared, and then we get 2x times dx over dt, right? So again, I did use the prime notation here with our product rule, but I remember I'm taking the derivative with respect to t, so that produced the dx over dt. And then v in the product rule, so this is kind of off to the side work here, will be h, and then v prime is going to be dh over dt. Question?
dx over dt.
Because this, I didn't write it, but we're taking the derivative with respect to t here. So since x is a different variable than t, it's going to kick this dx over dt out. Same here is why this became dh over dt as opposed to just 1. It's a great question though. And probably using my little prime over here with this probably makes it not as clear. I tried to do a better job there. But we good then? Now we have our pieces. So the product rule, we get x squared dh dt plus 2hx dx dt. Maybe look at that, might be a way to look at it. So at this point, we have our derivative function, but we're asked to solve for dx over dt. So what we're going to do, I'm going to just think about if you're back in Algebra 1 and you have 7 plus 2x equals 13. First thing you do is subtract 7, right? That's the first thing we're going to do here as well. So we're going to get dv over dt minus x squared dh over dt equals 2hx dx over dt. So again, the variables get a lot weirder looking, but we're just doing algebra. So now at this point, I need to get rid of this 2hx. Right? We could divide. I'm going to say again, let's multiply by the reciprocal, but it'll actually will multiply this whole side, so it kind of gets a little weird looking. It would be 1 over 2hx dv over dt minus x squared dh over dt equals, since we multiplied by the reciprocal, that's 1 over 2hx times 2hx dx over dt. Those will cancel. That's not a bad looking piece. You could work with that, right? So then we get that dx over dt is equal to 1 over 2hx dv over dt minus x squared dh over dt. So what we're going to do when we start actually doing related rate problems is you're going to know these rates and you're going to fill them in. They're just going to be numerical values and be able to solve this. Okay. Any questions on that one? So this is a lot like 4 on your paper there. So if you want to go ahead and try that, we can take a look at it. Okay, so let's look at another example. This is from the attached worksheet here. This is number 4. So if you haven't given it a try, make sure you do that. We're asked to find dv over dt if v equals pi over 3 r squared h. Right, so we see here we have two variables. We know we're going to have to use the product rule. It's kind of annoying. Later on, when we start to do a little more applications, if you ever have a chance to replace, say, h with r, it would be a really nice substitution to make before you do the derivative, because then you're down to one variable. It makes it a lot easier. We don't have that luxury here. So for this one, we'll take the derivative with respect to t of both sides. Now, pi over 3 is a constant, so I'm going to just go ahead and set it out in front there now, but I could have done it later. It doesn't matter. So now we have this derivative with respect to t of r squared h. So this is a case where we have another product rule. Okay. Now, let's see how that looks. So the left-hand side is dv over dt. So pi over 3 is just, it's a constant multiple, so it just sticks around. Whatever, though, we do with this product rule, this is going to get, the pi over 3 would get distributed into that. It's going to hit each term of it. Now, we might avoid ever having to do that, or we might not actually distribute it, but we need to put the parenthesis there to indicate that. So if our u function is r squared, so if you do u times the derivative of h, right, plus the derivative of r squared, which is 2r dr dt times h, right? So a product rule there. So this is u prime, this is v prime. So you might try, if you feel confident, you could try it sometimes without writing out the u's and v's. But if you need to, that's fine too. So now at this point, we were asked to find dv over dt.
Then you already have it.
We kind of have it, yeah.
I put the H in the R.
Yeah, I think I put the h over and call it a day.
Do that kind of thing.
Now, if I hope you noticed on the function that we use for the next problem is the same exact function. So okay, so this is what we would get for our answer for number 4. Okay, for number 5, let's go ahead and do that while we're here. We're asked to find same piece, same function, but we're asked to find dh over dt. So you're going to start the same way. You're going to take the function that we know for the volume of a cone. We're going to take its derivative. Now we got this big mess down here. So we're going to, this was the answer to that one, but now we're trying to isolate dh over dt. Bunch of ways to do it. You could distribute pi over 3. I don't think that's a good idea. It seems like a lot of work. So let's go ahead and get, this is a multiple. I'm going to go ahead and multiply both sides by its reciprocal. So that'll give us 3 over pi times dv over dt equals r squared dh dt plus 2h dr over dt. They looking okay? Yeah. There's the square. Okay. So we have this. All I did was I just multiplied by 3 over pi on both sides, and it made this piece go away. Now, I need to isolate this piece, correct? This is an additional term. The easiest way to get rid of that is just subtract it. So let's subtract it. So 3 pi times dv dt minus 2rh dr dt equals r squared dh dt. You could divide by r squared, but this is already a fraction. Like, because dv over dt, it's written as a fraction, but it's actually going to be a rate. But I'm still going to multiply by 1 over r squared and just leave it outside of a parenthesis. So I'm going to say 1 over r squared times 3 over pi times dv dt minus 2rh dr over dt equals dh over dt. Now, that's probably about as, I guess, yeah, I would just leave it like that. Because again, you're going to be plugging, so what's going to happen here is what we're going to look at is you're going to have some cone, right? It's going to have some initial radius and some initial height, right? And then you're going to know the change in volume and the change in the radius, and that's going to give us a measurement for the change in height. Is what's going on there. Is why it's such a mess. But at some point, once we get the derivative here into a decent form and done, you're going to be putting in a number and calculating something. So kind of look at that. So yeah, so there we go. Any questions there?